Hello everyone, welcome to this video on resistors in series and parallel. Okay, so you should at this stage have done this or looked at the short video on the basics of electricity. Now we're going to have a look at resistors in series and in parallel. So first of all, what do those two terms mean? Well, series is like a TV series. Even if you binge watch a TV series, you watch one episode, then you watch the next episode, then you watch a third episode, etc., etc. You watch them in order. And in what that means for electricity is that if you have a series arrangement of resistors, the current will go through one resistor, then through the next one, then through the next one. Okay, it does them in turn. It would be the same current going through each resistance. Whereas if you wanted to watch things in parallel, well, then you would need sort of a split screen or loads of screens where you could watch one episode, if you want one episode in one screen and another episode in another screen. Okay, and I know people do this with football matches. You can maybe be following 3 or 4 football matches at the same time, watching them on separate screens. Okay, that's a parallel experience. So you can see instead of 4 football matches taking you 4 times an hour and a half, you get to see all four matches in one period of 1.5 hours. Okay, but that's, maybe you don't get the same experience. You're losing out on something. And so we'll look at what happens when we talk electrically about what happens electrically when you have things connected in parallel is the current splits up, just like your attention is split between 4 screens, say if you've got four matches on. So the electricity splits, the current splits between the 4 resistors. Part goes one way, part that way, part this way, and part the 4th way. Okay. So we've done enough sort of, V equals IR is going to take us a long way with electricity. So we're going to just analyze our series and parallel circuits using Ohm's law. And hopefully if you follow the derivation of the basic equations for series and parallel, you'll get an insight into how Ohm's law works. And as I said in a previous lecture, Ohm's law is kind of deceptively simple in that it looks like a simple equation, but you have to understand how it works in order to apply it properly. Okay, so we'll look at resistors in series first, and we'll obtain a simple equation. In fact, it's an incredibly simple equation. So if we have a power supply connected to 2 resistors, and the question we're going to ask ourselves is, what's the total resistance of that circuit? The power supply, or the supply voltage, I'm going to call the supply voltage Vs, right? And I'm going to do my color coding again. So I'm going to get rid of that black line and draw in my red, because I know the potential here is going to be whatever the potential of the back. Remember, that's the plus side, that's the negative on the far side. So whatever this potential is, this voltage is, that's the potential here. So I'm going to put that as plus Vs. And we know where the black line is, that is 0 volts. Now there's a bit of confusion in the center, so I'm just going to label that. I'm going to use a different color again. I'm going to make that blue, because we're not sure at this stage what that potential is going to be. And we want to also measure potential differences. So we're going to measure potential difference, and we're going to look at the potential difference across each resistor. We'll say that's VR1 between there and there, and VR2 between there and there. And the whole potential difference is the difference between there and there. And hopefully you'll agree with me, the potential here is Vs, the potential there is 0. So this whole one should be just equal to Vs. Okay. So what can we do with that? We also know that the same current flows everywhere through this circuit. So the current is going to be capital I there, and it's everywhere capital I. We're going to represent it by capital I. All right. So this is a series circuit, by the way, because what happens? The current comes in, all of it goes through R1, and then all of it goes through R2. Okay, so it's going through the resistors in series, and it's the same current in both resistors. So how do we make some progress here? So we're going to start thinking about the two resistors together. We want to know what the total resistance of the circuit. So for the whole circuit, we can say, if we talk about the whole circuit, and this is crucial about Ohm's law, you can apply Ohm's law to an individual element of the circuit or to the whole circuit. So we're going to apply it to the whole circuit first. If we apply it to the whole circuit, we say Vs equals I or T. The supply voltage equals the current times the total resistance. We're trying to get a value for RT. Now we're going to apply it to R1. So VR1, VR1 equals the current flowing through the resistor I multiplied by the size of the resistor R1. And then we're going to apply the Ohm's law to R2. VR2 equals the current flowing through it, I, times its resistance. Okay. Now we want to figure out what is RT equal to. Okay, now we can use, how can we use this? Hopefully you'll see that the electricity coming along here is going to lose some energy over R1 and then the rest of the energy over R2. So it's going to have a drop in potential here and then the remaining drop in potential there. So Vs equals VR1 plus VR2. So that's the total drop in potential. It's going to drop some there and the rest there. So that has to be true. But we've got equations for each of these. So that's IRT equals IR1 plus IR2. Now you see I appears in all of these. That means it's a common factor. And if we divide each side of the equation by I, it disappears. And we end up with a very simple equation that the total resistance, when you have two resistors in series, you just add the resistors together. Okay, very, very simple formula. And that works if you've got three resistors in series, you add the three resistances together. Okay, very straightforward. Now, there's this quick calculation in the, or quick question in the notes. So I'm just going to share the screen so we can have a look at the notes there. Okay. And you'll see at the bottom of, is it page 20? Yeah, bottom of page 20, we have a circuit there with a 15-volt power supply or 15-volt battery, probably a battery pack, connected to three resistors in series. How do I know they're in series? Because the same current is going to flow in turn through each resistor. So once I know that it's a series circuit, I know I have the equations to sort it out. Okay, so I'm going to do that calculation for you now on the whiteboard. All right, so we'll stop sharing. Pardon me, I've got a attack of something or other there. So we'll clear this off and I will just draw the circuit briefly to get us started. Again, if you're doing these, it's a good idea to draw the circuits, but don't spend a lot of time. I wouldn't be getting a ruler out and doing something like that there. So in a test or anything, just sketch it down as quickly as you can and then move on. Okay, so part one says, what's the total resistance? Well, resistors in series. They're clearly in series. So that current there will go through that resistor, then through that resistor, then through that resistor, and back to the battery. So part one, RT equals R1 plus R2. Now there's three resistors, so you add all three together. So that's 200 plus 300 plus 500, and we get 1,000. Nice even number, 1,000 ohms. Okay. Part two, what's the current? Now, for this part, you basically always, generally, any question that I ask you, the second part will tend to be, well, what's the current at the battery? Because unlike this question, in other circuits, the current will change from point to point in the circuit. So to work out the current at the battery, apply Ohm's law to the whole circuit. So it's Vs equals IRT. The supply, that's 15 equals I times 1,000. 15 over 1,000 equals I is equals 0.015. Remember, I is a current is measured in amps. And you could write that down as 15 milliamps. Okay, so we're up and running. We got the first two parts done. Now, I generally get the students in class to attempt this question, and this is where part three is where they start to get a little bit unstuck. It says the PD across each of the resistors. Now, so what it's asking you, we know the potential here is going to be 15 volts, and we know the potential there is going to be 0 volts. What's going on in here? It's kind of messy. Now, here I applied Ohm's law to the whole circuit. But now I'm going to apply Ohm's law to each individual resistor. So I'm going to apply it to the 200 ohms, then to the 300 ohms, then to the 500 ohms. So to point out that I'm just dealing with the 200 ohms, I'm just going to do V200, which means the potential difference across the 200 ohm resistor. That equals I times R. What's the current flowing through it? What's that? And what is the size of the resistance? It's 200. And what we get from that is, I think if I've done my maths correctly, is 3 volts. V300, now applying it across to that resistor, IR equals 0.015 times 300. And you get 4.5 volts. And finally, the 500 ohm resistor, you get 7.5 volts. Okay, a good thing to do at this stage is add those up. The potential difference across, remember, the potential difference across that plus the potential difference across that plus that has to add up to 15. 7.5 and 4.5 gives me 12 and 3 gives me 15. So that's working out well. Okay, and then the last part, again, another stumbling block for people, the potential at each point in the circuit. So, okay, so we know the potential here, out here, all along here, this is plus 15 volts. So what's the potential there? And what's the potential there? You need to work out those. We know the potential there is 0 volts. But we know the potential difference across that resistor. We've worked that out. It's 3 volts. If it starts off as 15 there, it's going to drop energy, and there's a 3 volt difference there. That means that at this point, you're going to have 12 volts. 15 minus 3 equals 12. And then further on here, it's 12 here. And the potential difference across that resistor is 4.5. So the potential there is 7.5. Oh yeah, I should have put the unit in there as well. And of course, my final check on have I done this right is the potential difference in there and there should be 7.5. So it's this value 7.5 minus 0, which gives me 7.5. That's worked out pretty well. Okay. So that's how we analyze series circuits. Series circuit, just to remind you again, is where you have each device in the circuit, the same current passes in turn through each. Okay. Now you may think, great, that's fine. Surely that's all we need. Okay, but it isn't all that we need. A real problem with series circuits is that if, say, it's the classic Christmas lights problem. You probably you're maybe too young to worry about Christmas lights or care, but there is this problem that if you have a whole series of lights connected in series, if one bulb fails, then that stops the current flowing everywhere. Okay, and so, you know, any lighting circuit should be connected up in a way that if one bulb fails, the other lights all still work. And the way that you do that is connect things in parallel. Okay, so in this section, we're going to look, so generally circuits can be a mixture of things in series and things in parallel. So in this section, I'm now going to go on to looking at parallel circuits. Okay. We're going to do a very similar thing to what we've just seen. We'll analyze the circuit. Now, remember I said that if you watch sort of matches in parallel, your attention gets divided up, and that in a parallel circuit, the current gets divided up. So this is what we mean by connecting in parallel. So I'm showing two resistors connected in parallel. Now, please don't get it into your head that the resistors have to be parallel to each other for them to be in parallel. That's not the issue here. For them to be in parallel, the current has to split up, go through the two resistors, and then recombine. Okay, so you have the full current here, and then we'll call that R1 and R2. So this becomes I1 and I2. And that's I1 and I2, and then it comes back to being the current here. This is still VS. And before we derive anything, again, a color diagram helps here. I'll draw in the battery as usual, and then we'll link points. So the positive side of the circuit I'll do in red. Okay. All of those points are at the same potential. How do I know that? Because they're all connected by simple wires. Then I'll do in the resistors. And then we do the final part of this, they connect back to the battery, the negative of the battery. So the potential here is plus Vs, and the potential over on the far side is 0. And that's Vs there. So everything on this side, the positive is plus Vs, everything over on that side is at 0. So hopefully you can see what's the potential difference across that resistor. We'll just label it R1 and R2. What's the potential difference across there? Well, that's Vs, and that's 0. So you get the voltage from the source directly across that resistor. What's the potential across that resistor? It's the same, equals Vs. So you can get the same voltage across a load of resistors in a circuit. Now again, these resistors could be light bulbs, they could be heating filaments, they could be a whole series of things. Okay, in an electric device. So the current out here is the full current I. That splits up and you have I1 going through R1, I2 going through R2, and then they recombine and the current goes back to the circuit, goes back to the battery. So as we did in the last, I'll just label that I1 and that I2. So we're going to apply Ohm's law. I'll just get rid of this circuit altogether now. We're going to apply Ohm's law to the whole circuit. When you apply Ohm's law to the whole circuit, Vs equals I. Okay, so we're talking about sort of the current around the battery here. Vs equals I times the total resistance of the circuit. And then we're going to apply Ohm's law to each of the individual resistors. Same principle as last time. So look at that resistor. The voltage across it is Vs again, and it's equal to I1 R1. And this resistor, the voltage across it is Vs, and that's equal to I2 times R2. You'll see we have Vs common there. Now the other equation we have, the other bit of information we have, is the current here is I, and it splits up. Part of it goes that way, and part of it goes that way. So hopefully you can see that I has to equal I1 plus I2. The current out here splits up. It could be half that way and half that way. It depends on the value of these two resistors. But some of it goes that way, the rest of it goes that way. Okay, so I equals I1 plus I2. Now, we can go back up here and get an expression. You'll see that if I bring RT across, it goes under Vs. Vs over RT equals I. This one, Vs over R1 equals I1. And here, R2 can go under Vs, and you get I2. So we're going to replace I1, and I2 by these three expressions here. So Vs over R, sorry, that's for the whole circuit, so that's RT, equals Vs over R1 plus Vs over R2. That's a common factor. And you might think, oh, we're going to end up with RT equals R1 plus R2 again. No, you don't. It's a very different result. 1 over RT equals 1 over R1 plus 1 over R2. And if there were three resistors in parallel, it would be 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3. Okay, so that's resistors in parallel. That's the value you get. Just one thing, a couple of things to be aware of. When resistors are in series, when you add extra resistors in, you increase the resistance. When resistors are in parallel, the more resistors you add in parallel, the lower the resistance becomes. You're adding extra paths, extra ways that the current can get around the circuit, and that makes it actually easier for the current to flow. So you get a lower current. Okay, and just to bed in that equation and those ideas, we're going to do again another calculation from the notes, and then we're finished for today's presentation. Okay, so I'll just share the screen with you to have a look at that question again. Again, all I've been going through is in the notes there. You can have a look at that. And it's question 10. For the previous circuit, okay, so we're going to have resistors, two resistors in parallel. One's 200 ohms, the other's 100 ohms. And the power supply provides an EMF of 20 volts. Determine the total resistance of the circuit, the current of the battery, PD across each resistor, and the current through each of the resistors. Okay, it's quite a simple calculation, but we'll just work on it as I turn you around. I'll stop sharing now so we get a good image of the of the board. So again, this is the important equation. This is the one we're going to apply, particularly in the first part of the calculation. So I'm just going to redraw a circuit. So it says it's a parallel circuit with R1 and R2 with so we've got 200 ohms and 100 ohms. We've got I out here and I1 there and I2 that way. Okay, and we've got I coming back here. The power supply is 20 volts. So the potential around here is all going to be 20 volts, plus 20 volts. And the potential around here is going to, as always, 0 volts. So part one. Find the total resistance of the circuit. So these two resistors are in parallel. Again, how do I know they're in parallel? Because the current flows through, comes down, splits, and goes between each resistor and then recombines. Okay. Because of that, we have to use 1 over RT equals 1 over R1 plus 1 over R2. 1 over RT equals 1 over 200 plus 1 over 100. Now I'm just going to talk you through something quite useful here for this calculation. Those are easy enough to work out what 1 over 200 and 1 over 100 is on your calculator. Sometimes the calculation won't be as straightforward. So in general, I like to use my calculator to use these. This calculator has an x to the -1 button there. Some of you may have a calculator that is a 1 over x button. X to the -1, by the way, is the same as 1 over x. Okay, so we have 1 over here. So the way I'm going to work this out, I'm going to put in 200, 2, 0, 0. Okay, then I'm going to press the x to the -1 button. Okay, so what I've effectively written in there is 1 over 200 plus, and I'm going to type in 100. So you see that. I'm going to press my x to the power -1 button. Okay, so that's 200 to the power -1 plus 100 to the power -1, 1 over 200 plus 1 over 100 equals. And okay, it's coming up as a fraction. I get it as a decimal. It's given me 0.015. Okay, now the thing to be aware of from this is that 0.015 is not RT. I have worked out 1 over R1 plus 1 over R2. 1 over R1 plus 1 over R2 equals 1 over R2, RT. 1 over RT, not RT itself. To get RT, and this is the handy thing about using it on the calculator, is without putting numbers in or anything, I just hit the x to the -1 button again, and then equals, and the answer is 200 over 3, or just to convert it to decimal, 66.67. Okay, so I'm just going to write that down. So RT equals 66.67 ohms. Okay, so a big mistake there, that's commonly made, is when I did the 1 over 200 plus 1 over 100, I got 0.015. So often I see students write down 0.015 as the total resistance in that case. But the answer, we have one resistance is 200, one resistance is 100. The combined resistance tends to be below, but not a huge amount below, the lowest resistance in the circuit. So you can see the lowest resistance we have here is 100. So when they're in parallel, the combined resistance will be beneath 100, but not a huge way beneath 100. Okay, so it won't go down to 0.015. it'll go down, in this case, to 66.67. Okay, so that's part one. What's the current? Again, the current at the back, we just apply Ohm's law to the whole circuit. We always do it this way. So it's Vs equals IRT. So what have we got? 20 is the supply voltage equals the current multiplied by 66.67. 20 divided by 66.67 equals I, which equals, I've already got, okay, so if I divide that by 20 equals, inverse equals, and I get 0.3. So the current there is 0.3 amps. The PD across each of the resistors, now remember, if we think of that all the way out here, the potential there is 20 because it's connected by a simple wire all the way back to the battery, and the potential here is 0. And the same thing goes for there and there. That's at 20 volts, that's at 0 volts. So the PD here is 20 volts. So V200 equals 20 volts and V100 equals 20 volts. Now, how do I work out the current at each resistor? Or should I know I'm looking at the wrong question, folks. Sorry about that. It's getting late, getting tired. Okay, so PD across each of the resistors, the current through each of the resistors. So what's the current in each resistor? And if you're asked about an individual resistor, apply Ohm's law to that individual resistor. So we'll take the 200 ohm one first. 200 ohms, apply Ohm's law. The voltage across it equals the current going through it times its resistance. So that is 20 equals I1 times 200. 20 over 200 equals I1, which equals 0.1 amp. Okay, so that's the current flowing through the top arm. Now we know the current here is 0.3 amps. 0.1 amp goes that way. So we can say fairly certainly that the 0.2 amps, the rest of the current must have gone that way. There's no other possibility. But anyway, we'll carry on for part 4 and say 100 ohms. What's going on there? Apply Ohm's law to that. V equals IR. So this is I2R2. So the potential there is 20. Potential there is 0. So it's 20 volts across that resistor equals I2 times 100. 20 over 100 equals I2. And you get 0.2 amps. Again, another reassurance that we've done everything correctly. The current out here is 0.3 amps. And then when it gets in here, there's 0.1 amp goes up that way, and 0.2 amps goes that way. And just to note as well, the big resistance has the smaller current flow, and the smaller resistance has the bigger current flow. When you multiply the I by R, the current by voltage by resistance together, you get the same voltage. So resistors in series, in parallel, always have the same voltage across each other. Okay, so it's got dark outside there, so I've been talking for long enough, so I'm going to end there. So you should be in a position to attempt the lab for your next experiments, where you'll do Ohm's law and resistors in series and parallel. 3 simple circuits to put together, and you learn how to use a digital multimeter, and you draw graphs in each case and use the graph to work out the value of the resistor in each case. It's repetitive, but that's useful in its own regard for you understanding how to put circuits together. Okay, so I hope you find this useful. Take care, and if anybody has any questions, just drop me an email, and I'll get back to you as soon as I can. All the best.